Learning objectives. In this chapter, the user would learn the following in detail: parameter estimation, random sample, statistic estimator, unbiased, method of moments, maximum likelihood estimation, confidence intervals, sampling from normal population, distribution of the sample mean, population variance is unknown, sampling from Bernoulli distribution, hypothesis testing, null hypothesis, alternative hypothesis, tests on population mean, hypothesis concerning two means, goodness of fit, chi-square test. Likelihood equations. However, in some cases, as in the above example of the gamma distribution, the likelihood equations may be intractable without computers. Method of moments. Whereas the method of moments estimators can be quickly and easily calculated by hand. Estimates by the method of moments may be used as the first approximation to the solutions of the likelihood equations, and successive improved approximations may then be found by the Newton-Raphson. In this way, the method of moments and the method of maximum likelihood are symbiotic. In some cases, infrequent with large samples but not so infrequent with small samples, the estimates given by the method of moments are outside of the parameter space. It does not make sense to rely on them then. That problem never arises in the method of maximum likelihood. Also, the estimates by the method of moments are not necessarily sufficient statistics. That is, they sometimes fail to take into account all relevant information in the sample. When estimating other structural parameters, example, parameters of a utility function instead of parameters of a known probability distribution, appropriate probability distributions may not be known, and moment-based estimates may be preferred to maximum likelihood estimation. Maximum likelihood estimation. Maximum likelihood estimation is denoted by MLE, is a method of estimating the parameters of a statistical model. When applied to a data set and a given statistical model, maximum likelihood estimation provides estimates for the model's parameters. The method of maximum likelihood corresponds to many well-known estimation methods in statistics. For example, one may be interested in the heights of adult female penguins but be unable to measure the height of every single penguin in a population due to cost or time constraints. Assuming that the heights are normally Gaussian distributed n, distributed with some unknown mean and variance, the mean and variance can be estimated with MLE while only knowing the heights of some sample of the overall population. MLE would accomplish this by taking the mean and variance as parameters and finding particular parametric values that make the observed results the most probable given the model. Maximum likelihood. In general, for a fixed set of data and underlying statistical model, the method of maximum likelihood selects the set of values of the model parameters that maximizes the likelihood function. Discrete random variables. Intuitively, this maximizes the agreement of the selected model with the observed data, and for discrete random variables, it indeed maximizes the probability of the observed data under the resulting distribution. Maximum likelihood estimation. Maximum likelihood estimation gives a unified approach to estimation which is well defined in the case of the distribution and many other problems. Confidence intervals, and gives a range of values for the parameter interval estimates or intervals within which the parameter is expected to fall with a certain degree of confidence. Because 95% of the sample means lie within 1.96 standard error of the population mean, 95% of the time we will choose a random sample whose mean is less than or equal to 1.96 standard errors, always from the population mean. Hence, an interval spanning 1.96 standard error either side of our sample mean will contain the population mean for 95% of all random samples. For 95% of samples, the interval x minus 1.96 standard error, x plus 1.96 standard error contains the population mean. The interval sample mean plus or minus 1.96 standard errors is a 95% confidence interval for the population mean. For 95% of samples, the 95% confidence interval will contain the population mean, but we only have one sample and one confidence interval. We will not know whether this interval contains the population mean or not. We only know that for 95% of random samples, it will. Note, for 5% of random samples, the interval will not contain the population mean. Usually, a 95% confidence interval is given. We are 95% confident that the 95% confidence interval contains the population parameter. The edges of the confidence interval are known as confidence limits. A 99% confidence interval is constructed by taking the interval sample mean plus or minus 2.58 standard errors. We are 99% confident that is interval will contain the population mean. An 80% confidence interval is constructed by taking the interval sample mean plus or minus 1.28 standard errors. We are 80% confident that this interval will contain the population mean. Note that the more confidence we are that the interval contains the population value, the wider the confidence interval. For example, refer Landau, H. et al. Cross-sectional and longitudinal study of the pituitary thyroid axis in patients with thalassemia, major clinical endocrinology, 1993, 38, 55-61. Ferritin levels, UG bar level, were measured in 37 patients with confirmed beta thalassemia major. The mean value was 2745, standard deviation 1030, standard error equal to 1030 divided by square root of 37 equal to 169.35. A 95% confidence interval for the population mean is given by 2745 plus or minus 1.96 into 169.35 equal to 2745 plus or minus 331.93 equal to 2413, 3077. A 99% confidence interval for the population mean ferritin level is wider and more likely to contain the true population value and is given by 2745 plus or minus 2.58 into 169.35 equal to 2745 plus or minus 436.92 equal to 2308, 3182. For normal individuals, ferritin levels rarely rise above 100 μg per liter. Hence, using either confidence interval, it can be seen that mean ferritin levels appear to be grossly elevated in this group of patients. Confidence intervals attach a level of precision to a sample estimate to help facilitate interpretation. By considering the confidence limits, ends of the confidence interval, the researcher is made aware of the extreme population scenarios with which the sample is compatible. For example, the sample of 37 ferritin levels allowed a guesstimate to be made with 95% confidence that the average level for the population lay somewhere between 2413 and 3077. In this interval is too wide to be clinically useful, then the sample size could be increased, leading to the standard error being reduced and hence a narrower confidence interval. For 95% of samples, the interval x minus 1.96 standard error, x plus 1.96 standard error contains the population mean. Statistical inference. Statistical inference is the process of drawing conclusions from data that are subject to random variation. For example, observation errors or sampling variation. Statistical inference, statistical induction, and inferential statistics are used to describe systems of procedures that can be used to draw conclusions from data sets arising from system affected by random variation, such as observational errors, random sampling, or random. Initial requirements of such a system procedures for inference and induction are that the system should produce reasonable answers when applied to well-defined situations, and that it should be general enough to be applied across a range of situations. Inferential statistics are used to test hypotheses and make estimations using sample data. Parametric methods. Statistical inference means drawing conclusions based on data. There are many contexts in which inference is desirable, and there are many approaches to performing inference. Statistical inference means drawing conclusions based on data. One context for inference is the parametric model, in which data are supposed to come from a certain distribution family, the members of which are distinguished by differing parameter values. The normal distribution family is one example. One tool of statistical inference is the likelihood ratio, in which a parameter value is considered consistent with the data if the ratio of its likelihood to the maximum likelihood is at least some their hold values such as 10% or 1%. While more sophisticated inferential tools exist, this one may be the most straightforward and obvious. Random sample. A random sample of size n from a finite population of size n by n is a sample chosen without replacement, so that each of the possible samples is equally likely to be selected. If the population is infinite, or equivalently, if the sampling is done with replacement, a random sample consists of n observations drawn independently with replacement from the population. Maximum likelihood. Hereafter, we assume that either the population is infinite or else that n is sufficiently large compared to n that we can ignore the effects of having a finite population. Discrete random variables. Intuitively, this maximizes the agreement of the selected model with the observed data, and for discrete random variables, it indeed maximizes the probability of the observed data under the resulting distribution. Statistics, such as the sample mean obtained from random samples, can be thought of as random variables, and hence they have distributions called theoretical sampling distributions. In order for our inferences to be valid, it is critical that we get a random sample as defined above. Suppose that a random sample of size n is taken from a population having mean mu and standard deviation sigma. Although mu and sigma are fixed numbers, their values are not known to us. Statistics is the study of the collection, organization, analysis, interpretation, and presentation of data. It deals with all aspects of data, including the planning of data, collection in terms of the design of surveys and experiments. When analyzing data, it is possible to use one or both of statistics methodologies, descriptive and inferential statistics in the analysis data. Sampling in statistical inference. The use of randomization in sampling allows for the analysis of results using the methods of statistical inference. Statistical inference is based on the laws of probability and allows analysts to infer conclusions about a given population based on results observed through random sampling. Two of the key terms in statistical inference are parameter and statistic. A parameter is a number describing a population, such as a percentage or proportion. A statistic is a number which may be computed from the data observed in a random sample without requiring the use of any unknown parameters, such as a sample mean. A statistical model is a representation of a complex phenomena that generated the data. It has mathematical formulations that describe relationships between random variables and parameters. It makes assumptions about the random variables and sometimes parameters. A general form, data equal to model plus residuals. Model should explain most of the variation in the data. Residuals are a representation of a lack of fit, that is of the portion of the data unexplained by the model. Point estimation and interval estimation and hypothesis testing are three main ways of learning about the population parameter from the sample statistic. An estimator is particular example of a statistic which become an estimate when the formula is replaced with actual observed sample values. Point estimation equal to a single value that estimates the parameter. Point estimates of single values calculated from the sample. Unbiased. If the sampling distribution is known, then the ability of the sample statistic to estimate the corresponding population parameter can be determined. Biases estimate of distribution. Unbiased estimate of distribution. In particular, the sampling distribution determines the expected value and variance of the sampling statistic. If the expected value of the statistic is equal to the population parameter, the estimator is unbiased. If the variance of the statistic is small and it is also unbiased, then an observed statistic is likely to be close to the population parameter. Bias equal to distance between parameter and expected value of sample statistics. Subsequently, sample statistics can be classified as shown in the diagram. Average of the sample statistics. Statistical inference, population parameter usually unknown. Sample statistics from different samples. Unbiased. Estimates have low bias because their average is near the population parameter, but have high variability because they are widely spread and a single sample value could be far from the parameter. Statistical inference. Estimates have bias because the expected value is not equal to the parameter. They also have high variability because they are widely spread out. Statistical inference. In this case, the estimates are biased because all of them are systematically higher than the population parameter. The sample statistics have, however, low variability because they are all close together. Statistical inference. In this case, the estimates have both low bias and low variability. Experimental design aims to simultaneously reduce bias and variability by producing a sampling distribution as shown in figure. Statistical inference. In general, inferences about the characteristics of a population are based on data from a sample. Statistical inference. If the sample is not representative of the population being studied, the sample statistic may be biased, so you cannot use it to make valid inferences about the population parameter. Statistical inference. To minimize bias, the sample should be chosen by random sampling from a list of all individuals in the relevant population. This list is called the sampling frame. It is essential. Statistical inference. For a simple random sample, the individuals are chosen in such a way that each individual in the sampling frame has an equal chance of being selected. This may involve using computer-generated random numbers to select the sample. Statistical inference. Example. Health survey conducted in the Hunter region, study population. All residents of the lower Hunter region, Newcastle, Lake Macquarie, Port Stephens, Maitland, Cessnock, aged 25 to 69 years. Statistical inference. Sampling frame. Electoral roll. Note, some bias is introduced here. Younger persons less than 35 years and migrants are less likely to be on the roll. Statistical inference. Sample selection. Sample chosen using computer generated random numbers, so each person on the electoral roll in this age group has a 1 in 100 chance of selection. Statistical inference. Non-response may differ from the response in many ways. Example, being less healthy, and this could lead to bias in estimates of the proportion of smokers, average, weight, etc. Statistical inference. Example 5. show that unbiased estimator is not unique. Solution. Let x1, x2, etc. up to xn be a random sample from a Poisson distribution with parameter lambda. Then we know that for each x1, mean is lambda and variance is also lambda. Let x bar equal to x1 plus x2 etc. up to xn divided by n. Then expectation of x bar is equal to 1 by n expectation of x1 plus x2 etc. up to xn. Then 1 by n expectation of x1 plus expectation of x2 etc. up to expectation of xn. Then 1 by n times of, we have to substitute the value for expectation of x. We know expectation of x is lambda. Then 1 by n times of lambda plus lambda at the end lambda. Then 1 by n times of n lambda equal to lambda. Also, expectation of s square equal to sigma square equal to lambda, where s square equal to summation I equal to 1 to n xi minus x bar whole square divided by n minus 1. Therefore, mean x bar is an unbiased estimator of lambda. Also, s square is an unbiased estimator of lambda. Statistical inference. Example 7. If t is an unbiased estimator of theta, show that t square is not an unbiased estimator of theta and square root of t is not an unbiased estimator of square root of theta. Solution. If t is an unbiased estimator of theta, then expectation of t equal to theta. Variance of t equal to expectation of t minus theta whole square, then expectation of t square minus theta square, but variance of t greater than 0. Therefore, expectation of t square minus theta square greater than 0. Expectation of t square minus theta square, that is, expectation of t square not equal to theta square. Therefore, if t square is not an unbiased estimator of theta square, variance of square root of t greater than 0, then expectation of square root of t square minus expectation of square root of t square greater than 0, then expectation of t greater than expectation of square root of t whole square. Expectation of square root of t whole square greater than 0, then expectation of square root of t greater than square root of theta. Finally, expectation of square root of t not equal to square root of theta. Therefore, if square root of t is not an unbiased estimator of square root of theta. Statistical inference. In parameter estimation, we assume that the distribution of the variable we are interested in is adequately described by a distribution with one or more unknown parameters. We attempt to estimate the population parameter using the sample data. Statistical inference. To emphasize the difference between sample and population, the parameters we wish to estimate are called population parameters. Estimates of the population parameters obtained from a sample are called sample statistics or sample estimates. Test of hypothesis. A statistical hypothesis is an assertion about the distribution involving one or more random variables. If this hypothesis completely specifies the distribution, it called a simple hypothesis. Otherwise, it is called a composite hypothesis. Null and alternative hypothesis. Let theta be the parameter involved in a population. Suppose we want to test the hypothesis h naught, theta equal to theta naught. Suppose beside theta naught, some other values of say theta equal to theta 1, theta equal to theta 2 are also possible values of theta. Then the hypothesis h naught, theta equal to theta naught, h1, theta equal to theta 1, hi, theta equal to theta I are called admissible hypotheses. To distinguish one from other, we call h naught, theta equal to theta naught as null hypothesis and any other hypothesis as alternative hypothesis. Critical region. Let C be the subset of the sample space which in accordance with the given test to the region of the hypothesis under consideration. Then C is called the critical region. One-tail test. The possible set of null and alternative hypotheses are h naught, mu equal to mu naught, h1, mu greater than mu naught. Then h naught, mu equal to mu naught, h1, mu less than mu naught. Again, h naught, mu greater than or equal to mu naught, h1, mu less than mu naught. Then h naught, mu less than or equal to mu naught, then h1 mu greater than mu naught, where mu naught is the hypothesized value. Two-tailed test. The null and alternative hypothesis for two-tailed test are stated as follows: h naught mu equal to mu naught, h1 mu naught equal to mu naught, where mu naught is the hypothesized value. In the above consideration of one-tail and two-tail test, we have taken the significance level alpha as 0.05. In the same way, we also consider alpha equal to 0.01. In such a situation, for one-tail test and two-tail test, the region of acceptance and region of rejection are given below. Procedure for test of hypothesis. Step 1. State the null hypothesis. Step 2. Decide the alternative hypothesis. Say one-tail or two-tail to be applied. Step 3. Choose the significance level alpha. Step 4. Calculate the test statistic z is equal to x minus expectation of x divided by standard error of x. Step 5. Find the table value of z and decide whether the sample statistic falls within the region of acceptance or rejection. Statistical inference. Hypothesis testing for a population mean. A statistical hypothesis test is a procedure for deciding between two possible statements about a population. The phrase significance test means the same thing as the phrase hypothesis test. Statistical inference. Number 1. We write null and alternative hypothesis. Number 2. Calculate an appropriate test statistic. Number 3. Determine a p-value associated with the test statistic. Number 4. Decide between the null and alternative hypothesis. State a real-world conclusion. Statistical inference. Quantitative response variables and means. We usually summarize a quantitative variable by examining the mean value. We summarize categorical variables by considering the proportion or percent in each category. Thus, we use the methods described in this handout when the response variable is quantitative. Again, examples of quantitative variables are height, weight, blood pressure, pulse rate, and so on. For one population mean, a typical null hypothesis is h0. Population mean mu equal to a specified value. We will actually give a number where it says a specified value, and for paired data, the null hypothesis would be h0, mu equal to a specified value. Typically, when considering differences, the specified value is 0. The alternative hypothesis might either be one-sided, a specific direction of inequality is given, or two-sided, a not equal statement. Statistical inference. Test statistics. The test statistic for examining hypothesis about one population mean. T equal to x bar minus mu naught divided by s divided by square root of n, where x bar equal to observed sample mean, mu naught equal to value specified in null hypothesis, s equal to standard deviation of the sample measurements, and n equal to the number of differences. Statistical inference. The test statistic for examining hypothesis about one population mean difference, that is paired data, t equal to xd bar minus mu naught divided by sd by square root of n, where xd bar equal to observed sample mean difference, mu naught equal to value specified in null hypothesis, s equal to standard deviation of the difference in the sample measurements, and n equal to sample size. Statistical inference. For instance, if we wanted to test for a difference in mean, sat math and mean sat verbal scores, we would random sample n subjects, record their sat-m and sat-v scores in two separate columns, then create a third column that contained the differences between these scores. Statistical inference. Then the sample mean and sample standard deviation would be those that were calculated on this column of differences. Notice that the top part of the statistic is the difference between the sample mean and the null hypothesis. The bottom part of the calculation is the standard error of the mean. Statistical inference. It is a convention that a test using a t-statistic is called a t-test. That is, hypothesis test using the above would be referred to as one sample t-test and paired t-test respectively. Statistical inference. Finding the p-value. In general, a p-value is the probability that the test statistic would learn as much or more toward the alternative hypothesis as it does if the real truth is the null hypothesis. When testing a hypothesis about a mean or mean difference, a t-distribution is used to find the p-value. Statistical inference. We have shown the table value here. Using the table value, we can easily reject our hypothesis or accept our hypothesis. This is a close cousin to the normal curve. T-distributions are indexed by a quantity called degrees of freedom, calculated as df. df is called degrees of freedom, equal to n minus 1 for the situation involving a test of one mean or test of mean difference. Central limit theorem. The central limit theorem states that given a population with a finite mean mu and a finite non-zero variance sigma square, the sampling distribution of the mean approaches a normal distribution with a mean of mu and a variance sigma square by n. As n, the sample size increases. The expressions for the mean and variance of the sampling distribution of the mean are not new and remarkable. What is remarkable is that regardless of the shape of the parent population, the sampling distribution of the mean approaches a normal distribution as n increases. Figure. A simulation of a sampling distribution. The parent population is uniform. The blue line under 16 indicates that 16 is the mean. Red line extends from the mean plus and minus 1 standard deviation. If you have used the central limit theorem demo, you have already seen this for yourself. As a reminder, figure 1 shows the results of the simulation for n is equal to 2 and n equal to 10. The parent population was a uniform distribution. You can see that the distribution for n equal to 2 is far from a normal distribution. Nonetheless, it does shows that the scores are denser in the middle than in the tails. For n is equal to 10, the distribution is quite close to a normal distribution. Notice that the means of the two distributions are the same, but that the spread of the distribution for n equal to 10 is smaller. Statistical inference. Chi-square test. Chi-square test is a statistical test commonly used to compare observed data with data we would expect to obtain according to a specific hypothesis. That is, chi-square is the sum of the square difference between observed. It is denoted by O, and the expected data is denoted by E, or the deviation D divided by the expected data in all possible categories. Procedure for testing the significance of the difference between the observed and expected frequencies. H0. There is no significant difference between the observed and the expected frequencies. H1. There is significant difference between the observed and the expected frequencies. The test statistic is chi-square equal to summation O minus E whole square by E. O is called observed data, E is called expected data. The expected frequencies are determined on the assumption that H0 is true. The number of degrees of freedom equal to n minus 1, where n is the number of classes. From chi-square table, we can find for a given degrees of freedom the table value of chi-square for a given significance level, say alpha equal to 0.05 or alpha equal to 0.01. Statistical inference. Conclusion. If the calculated value of chi-square less than the table value of chi-square, H0 is accepted, the significance level alpha. If the calculated value of chi-square greater than the table value of chi-square, H0 is rejected, the significance level alpha. Two groups of 100 people each were taken for testing the use of a vaccine. 15 persons contracted the disease out of the inoculated persons, while 25 contracted the disease in the other group. Test the efficiency of the vaccine using chi-square. Solution. H0, the vaccine is not effective. H1, the vaccine is effective. Observed frequency table. Using the question, we have filled the observed frequency table. Then, we know the observed data. We have to find out the expected data. After that, we have to subtract observed data minus expected data. Then we have to find out observed minus expected whole square. Finally, we have to divide our squared numbers divided by expected data. We getting the total 3.12. That is the value of chi-square. Chi-square equal to the formula is we know already. Summation. Observed minus expected whole square divided by expected equal to 3.12. N degrees of freedom equal to 1 is obtained by row minus 1 into column minus 1. Here we have 2 rows, 2 columns. Table value chi-square for 1 degrees of freedom equal to 3.84. Conclusion. H0 is accepted since the calculated value of chi-square less than the table value of chi-square. Hence, then vaccine is not effective. Example. In a survey of 200 boys, of which 75 intelligent, 40 had skilled fathers, while 85 of the unintelligent boys have unskilled fathers. Do these figures support the hypothesis that skilled fathers have intelligent boys? Use chi-square test. Solution. H0. The figures do not support the hypothesis that skilled fathers have intelligent boys. H1. The figures support the hypothesis that skilled fathers have intelligent boys. Then, observed frequency table is obtained by using the question. Then, as usual, we have to write our observed data. Then we have to find out the expected data. Then we have to subtract our observed minus expected. Then we have to square the differences. That is called O minus E the whole square. Then we have to divide our squared numbers. Divide by expected value. Then the final answer is 8.88. Then finally we can write chi-square equal to summation observed data minus expected data the whole square divided by expected data equal to 8.88. Conclusion. H0 is rejected since calculated value of chi-square greater than table value of chi-square. The data supports the hypothesis that skilled fathers have intelligent boys. Statistical inference. The sampling distribution of the mean was defined in the section Introducing Sampling Distributions. Mean. The mean of the sampling distribution of the mean is the mean of the population from which the scores were sampled. Therefore, if a population has a mean mu, then the mean of the sampling distribution of the mean is also mu. The symbol mu_m is used to refer to the mean of the sampling distribution of the mean. Therefore, the formula for the mean of the sampling distribution of the mean can be written as mu_m equal to mu. Distribution of sample means. The distribution of sample means for samples of size n equal to 41 when the population has a mean of 460 and a standard deviation of 100 is figure SAT-math sampling distribution of means samples size n equal to 41 standard error equal to 15.6. We can determine how likely it is that the class is a sample that came from the general population of those taking the SAT-math examination. Your sample mean is 589.39. We will conclude its very unlikely probability is within 16 decimal places of 0. To get a sample like this from the general population of those taking the SATMAT exam. Figure SATMAT sampling distribution of means samples size n equal to 41. A sampling distribution is a theoretical distribution of the values that a specified statistic of a sample takes on in all of the possible samples of a specific size that can be made from a given population. Statistical inference. Sampling from Bernoulli distribution. The nature of the binomial distribution makes it a sampling distribution. In other words, the value of the binomial random variable is derived from a sample of size n from a population. You can think of the population as being a set containing zeros and ones, with a 1 representing a success and 0 representing a failure. The term success does not necessarily imply something good, nor does failure imply something bad. The sample is obtained as a sequence of n trials, with each trial being a draw from the population of zeros and ones. Such trials are called Bernoulli trials. Example: on the first trial, you draw a value from 0, 1 with p of 1 equal to pi. Then you draw again in the same way and do this repeatedly a total of n times. So, your sample will be a set such as 1, 1, 0, 1, 0, 1. In the case for n equal to 6, this set has 4 ones and 2 zeros. So, the value of binomial random variable is y equal to 4. The value of the binomial distribution is the sum of the outcomes from the trials, that is the number of ones. In the theory of finite population sampling, Bernoulli sampling is a sampling process where each element of the population that is sampled is subjected to an independent Bernoulli trial, which determines whether the element becomes part of the sample during the drawing of a single sample. An essential property of Bernoulli sampling is that all elements of the population have equal probability of being included in the sample during the drawing of a single sample. Bernoulli sampling is therefore a special case of Poisson sampling. In Poisson sampling, each element of the population may have a different probability of being included in the sample. In Bernoulli sampling, the probability is equal for all the elements. Because each element of the population is considered separately for the sample size is not fixed but rather follows a binomial distribution. Statistical inference. The method of moments estimator for theta 1, theta 2, etc. theta k denoted by theta 1, theta 2, etc. theta k is defined as the solution if there is 1 to the equations. Mu1 hat equal to g1 of theta 1 hat, theta 2 hat, etc. theta k hat. Mu2 hat equal to g2 of theta 1 hat, theta 2 hat, etc. theta k hat. Finally, mu k hat equal to gk theta 1 hat, theta 2 hat, etc. theta k hat. One starts with the deriving equations that relate the population moments, that is, the expected values of powers of the random variable under consideration, to the parameters of interest. Then a sample is drawn and the population moments are estimated from the sample. The equations are then solved for the parameters of interest using the sample moments in place of the unknown population moments. This results in estimates of those parameters. The method of moments was introduced by Carl Pearson in 1894. Advantages and disadvantages of this method. In some respects, when estimating parameters of a known family of probability distributions, this method was superseded by Fisher's method of maximum likelihood, because maximum likelihood estimators have higher probability of being close to the quantities to be estimated and more often unbiased. Advantages and disadvantages of this method. In some respects, when estimating parameters of a known family of probability distributions, this method was superseded by Fisher's method of maximum likelihood, because maximum likelihood estimators have higher probability of being close to the quantities to be estimated and more often unbiased. The variance of the sampling distribution of the mean is computed as follows. sigma m square equal to sigma square divided by n. That is, the variance of the sampling distribution of the mean is the population variance divided by n, the sample size, the number of scores used to compute a mean. Thus, the larger the sample size, the smaller the variance of the sampling distribution of the mean. This expression can be derived very easily from the variance sum law. Let's begin by computing the variance of the sampling distribution of the sum of three numbers sampled from a population with variance sigma square. The variance of the sum would be sigma square plus sigma square plus sigma square. For n numbers, the variance would be n sigma square. Since the mean is 1 by n times the sum, the variance of the sampling distribution of the mean would be 1 by n square times the variance of the sum, which equals the standard error of the mean is the standard deviation of the sampling distribution of the mean. It is, therefore, the square root of the variance of the sampling distribution of the mean can be written as sigma m equal to sigma by square root of n. The standard error is represented by a sigma because it is a standard deviation. The subscript m indicates that the standard error in question is the standard error of the mean, standard deviation, standard error. Sigma is called standard deviation, m is called standard error. The population variance. The population variance is calculated by dividing the sum of squares of the differences by the number of items in the population, while the sample variance is calculated by dividing the sum of squares of the difference by 1 less than the number of items in the sample. This approach for the variance formula for the sample data produces a more reasonable and unbiased estimate of the population's variance than if the same formula was used. The difference in calculation population versus sample variance. When I calculate population variance, I then divide the sum of squared deviations from the mean by the number of items in the population. When I calculate sample variance, I then divide the sum of squared deviations from the mean by 1 less than the number of items in the population. This alteration of the variance formula for the sample data produces a better and unbiased estimate of the population's variance than if the same formula was used. Sigma square equal to summation I equal to 1 to n xi minus x average whole square by n. As a result, the calculated sample variance and therefore also the standard deviation will be slightly higher than if we would have used the population variance formula. Sigma equal to square root of summation I equal to 1 to n xi minus x bar whole square divided by n. Purpose population variance. The purpose of this little difference is to get a better and unbiased estimate of the population's variance by dividing by the sample size lowered by 1. We compensate for the fact that we are working only with a sample rather than with the whole population. Conclusion. In this chapter, we have covered the following in detail: parameter estimation, random sample, statistic, estimator, unbiased, method of moments, maximum likelihood estimation, confidence intervals, sampling from normal population, distribution of the sample mean, population variance is unknown, sampling from Bernoulli distribution, hypothesis testing, null hypothesis, alternative hypothesis, tests on population mean, hypothesis concerning two means, goodness of fit chi-square test.